Hey everyone, welcome to this video on electrical energy sources. Today we'll be exploring the different types of sources and how they behave in the circuits and how we can manipulate them and perform source transformation and some example problems related to them. So let's go into the topic. The electrical energy sources are mainly categorized as independent sources and dependent sources. Now, independent sources could be either a voltage source or a current source. And again, a voltage source or a current source could be an AC voltage source or a DC voltage source, or an AC current source or a DC current source. On the other hand, the dependent sources. Now, there are four types here. So, we could have a voltage controlled voltage source, a voltage controlled current source, a current controlled voltage source, and a current controlled current source. Don't worry, we'll be exploring each of these. We'll do some example problems with this, and the concepts would get clear. Let's look at the independent sources first. So, the independent sources, like we already saw, could be a voltage source or a current source. Let's consider both the ideal as well as the practical scenario. In the ideal scenario, a voltage source would be just represented by a circle with the positive and the negative terminals marked in it. What is the difference between an ideal and a practical voltage source? So, in the ideal voltage source, we assume that the internal resistance of the source is going to be zero. So, which means that R over here, R internal, is equal to zero. Now, what does a voltage source really do? A voltage source, it tries to maintain a constant voltage between two terminals. So there are two terminals A and B, and it will ensure that the voltage across these two terminals is always maintained at 10 volts. If we now try to plot a graph between the V and the I in this source, where V would be in the y axis and I in the x axis. So here the VI characteristics of this ideally would be in this manner. So no matter what happens to the current of the circuit because of the load which is connected to the circuit, uh, this voltage source will try to maintain the voltage at 10 volts. So this is the ideal situation. But practically that's not the case. So in practice, usually apart from this, we'll be having a resistor, the internal resistance R, which will be in series with this voltage source. So now this is the practical voltage source. So the VI characteristics of the practical voltage source would slightly be different as compared to the ideal voltage source, because there is going to be a slight drop of R into the current I which is flowing. So with the increase in current, there's going to be a drop. So practically this is going to be your voltage characteristics of the practical voltage source. As the I increases, R into I will increase. So the voltage available across the terminals A, B would be Vs minus R into I. So as this parameter increases, the value that is available across AB, which is say VAB, that is going to decrease. So there is a drop in the VI characteristics of this practical voltage source. Now coming to the current source. So an ideal current source will have the internal resistance as 0. So it is going to try to maintain the current flowing out of the terminal A constant. So this current source I2 is going to try to maintain the current coming out of terminal A to be constant at 2 amps. So now if I plot the VI characteristics of this ideal current source, where I is in the x axis and V is in the y axis. So this is how it will appear. At 2 volts, it's going to be consistent no matter what the voltage is going to be. So if I connect a load across this, some resistive load maybe, so that particular current is going to go and flow into this resistance, and that's going to cause a voltage drop over here. So no matter what this resistor's value is, it is going to differ, and that is going to lead to a different voltage drop. But no matter what it is, the current is always going to be at 2 amps. So that is what an ideal current source is going to do. In a practical scenario, this R is not going to be equal to 0. This time around, we are going to consider that the internal resistance is in parallel with this current source. So, if I have a current source I, then the internal resistance is depicted to be parallel with this current source. So, now this becomes my practical current source. And how does the VI characteristics of the practical current source differ from the ideal current source? So if this is my I and this is my V, so this was my ideal characteristics. So the practical characteristics would be like that. It will differ. So there's going to be a slight deviation in the practical characteristics of the current source. Let us now look at this concept called source transformation. Now, this is a technique which simplifies circuits by replacing the voltage sources with current sources and vice versa. So, we can change the value of this voltage source with an equivalent value of a current source. In order to do that, it is quite obvious that we need to apply the Ohm's law over here, because that is what is going to establish the relationship between the voltage and the current and the resistor. So these are the three elements that we can see over here. So we know that V is equal to I into R. Now suppose I have a voltage source that appears like this. This is a practical voltage source of 10 volts, which has an internal resistance in series with it, which has a value of 5 ohms. Now, suppose I want to replace this voltage source with a current source. So, to begin with, a current source or a practical current source would appear like that. The internal resistance should be in parallel with it, but we need to know what should the value of this current source be. We know that the internal resistance value is not going to change because it's the same battery that we are going to use. So the internal resistance will remain as 5. So the value of I can be found out as I is V by R. So we know the value of V is 10. We know the value of R, internal resistance, is 5 ohms. So the value of I here is going to be 10 by 5, which is 2 amps. So we can replace this practical voltage source of 10 volts with a 5 ohms internal resistance with a current source of 2 amps with a 5 ohms internal resistance in parallel with it. Now, if I had to convert the current source into a voltage source, even then I had to apply the same Ohm's law. This time around, I know the value of I here is 2 amps, and I know that R, the internal resistance, is 5 ohms. So then the value of the voltage source would be 10 volts. So, therefore, we can actually transform this current source into this voltage source, where the 10 volts voltage source will have this 5 ohms internal resistance in series with it. Now, these are some points that we need to remember while we perform source transformation. Firstly, the arrow of the current source should be ensured that is always directed towards the positive terminal of the voltage source. The second point is we cannot perform source transformation if the internal resistance of the source is 0 or if the internal resistance of the source is infinite. So these are very important points that we need to remember. The next 2 points need some discussion before we arrive at it. So consider that there are, say, three voltage sources that are connected in this manner. So say this is plus, minus, a plus, minus, and a plus, minus, and so on. So say this is V1, this is V2, and this is V3. So the three voltage sources are connected end to end. So they are said to be connected in series. Suppose I have another voltage source which is connected in this manner. This is V4. So you can apply the same concept that we apply for KVL by marking the voltage drop directions from positive to negative, and then find out the overall voltage V of this setup. So here V would actually be plus V1 plus V2 plus V3 minus V4. So here the voltage sources are connected in series, but these voltage sources cannot be connected in parallel unless they have the same potential. So unless V1 and V2 are having the same value of voltage, they cannot be connected in this manner in parallel with each other. So only if they are both having the same magnitude, they can be connected in parallel. So that's one thing that needs to be noted over here. The second thing is, uh, in case of current sources, when current sources are in parallel with each other, then they add up. For example, if this is a current source, say I1, this is another current source looking downwards, say I2, and another current source, maybe again looking upwards, so that's I3. So here, if we consider the current I, overall current at this node I, so that would be applying KCL at that point, plus I1 minus I2 plus I3. So that will be the current I. So the currents are going to add up only when the current sources are connected in parallel. The current sources cannot be connected in series unless they are identical. So again, these are the two very important points that we need to remember. Let us now look at this example problem. We need to find out the current. I'll call it IA. So the question says find IA, and we are going to use source transformation to do this. So here we can see there are two sources. One is the voltage source, 10 volts, with the 3 ohm internal resistance in series with it. And there is a current source of 2 amps with 8 ohms in parallel with it. Now I can replace this voltage source by a current source. So how can I do that? So I can replace this voltage source in this manner. So my arrow should point towards the positive sign of the voltage source, and the internal resistance should come parallel with it. So this is 3 ohms. So I'll keep it as 3 ohms. So what should the value of the current source be? So it should be V by R. So here V is 10 and R here is 3. So this 10 by 3 amps should be the current source value. Now we'll redraw the remaining circuit and keep it as it is without disturbing it. So this is 6 ohms. Here we have the current source and the internal resistance connected in this manner, wherein I can redraw it like this. Here, so this is my 2 amps and this is my 8 ohms. Because see, after all, say I'll call this as point A and I'll call this as point B. And since there are no components connected over here, this is also like point B. So instead of taking an extra wire and connecting it like that, I've directly connected the 2 amps current source from point A to point B, while I ensure that the direction of the current is maintained. So this is now my simplified circuit. Here I can see that there are two current sources that are connected in parallel, and there are three resistors that are in parallel with each other. So we can easily find out the equivalent resistance of this circuit. So R equivalent we know is equal to 1 by R1 plus 1 by R2 plus 1 by R3, the whole inverse. So when I replace it, I'll get 1 by 3 plus 1 by 6 plus 1 by 8, the whole inverse. So this turns out to be 1.6 ohms. Now, if we look at the current sources are connected in parallel in this manner. So, this is the first one, the 10 by 3 amps, and this is the second one, the 2 amps, which is downwards. So, if I want to find out the current here at point A, this node, then I can say it is going to be plus 10 by 3 minus 2 amps. So that effectively turns out to be 4 by 3 amps. So I can actually replace this entire circuit in this manner. I'll say that this is 4 by 3 amps current source connected in parallel with the resistance 1.6 ohms. So this is how we can simplify a large circuit by using the source transformation technique. So that's all with this today's video on source transformation. I hope you've understood the concept clearly. Please do subscribe to my channel to keep watching more such videos on circuit theory. In the upcoming video, we'll be discussing about dependent sources and how we can frame the KVL and KCL equations using the concept of dependent sources to simplify the circuits. So that's all for today's video. See you in the next one. Bye bye.